Okay, so let's go over the probability question I did yesterday, and now I corrected it this morning. So this one, I have the both the question and the answer key over here, and this is my corrected response. My actual, what is it called? Rough work. Let's just leave at that. It's not great. Missed several points on that. Okay, so inside here we have the first part. Let x be a discrete random variable whose expectation exists, and let b be an event such that p is greater than 0. Define e of xb, the conditional expectation of x given b. Okay, so this is pretty straightforward, I'd say. It's just e of x given b. Um, Basically, we just write this in terms of the definition of expectation, right? The x value and then the probability of that happening. And then because it's given b, then we have to write given b over here as well. So that's pretty straightforward. Part two, let IB be the indicator random variable of event B. Show that this is the case. Okay, so we see that this over here, we're gonna go with the right-hand side because it's more complicated. And we're gonna just simplify it down to the left-hand side because it's hard to know what to expand out, but if we want to shrink it down, it's relatively easier and we know what we need to do. So on the right-hand side, we start off with this. We just expand out the definition of the expected value so that it would be the sigma from of x times the probability of that happening with the indicator equals x, right? And specifically, we chose that x does not equal to 0. Why is that the case? So that in the next part, when we rewrite this as p x equals x and b, we kind of save the trouble of having the ambiguous case of when it's 0, because 0 wouldn't even contribute to this sum here, because when you add 0 to a sum, it doesn't make a difference. And over here, when it's 0, it's kind of hard to tell, but here we know that if x is equal to x and b, then we know that it's definitely the case, right? And then we have this over here. And then this is just P of x equals x and B of P of B. That's just the definition of P of x equals x given B, right? That's the definition of conditional probability. So then we just have the sigma of the x of this. So then this is by definition E of x given B, right? Pretty straightforward. Part three, let B1 to Bn be a finite partition of the sample space. Okay, so partition means that it's exhaustive, so it covers the whole range and there's no overlaps. So they're disjoint. State and prove the partition theorem for the expectation of x. Okay, so the partition theorem is pretty straightforward. E of x equals the sigma from 1 to n of E of x given B of I, P of Bi. That's pretty straightforward. Um, and the proof of this is that we know that B1 to Bn is a partition of the sample space, so that all of the sum of these should equal to 1, right? Obviously. Hence, when we do E of x is equal to E of x times 1, yeah, that's the whole thing. And then we can split that 1 into the whole partition. And by linearity of expectation, we can move the sigma of the thing outside of the expected value. And then we can further expand each of them into our BI. And then they are the probability of BI by the previous part. Because in this part, we saw that E of x, what is it called? E of x given like this thing is equal to this thing, right? So we just move P of B to the left-hand side and we will have this expression. So this is already proven from earlier. So we're done for part A. For part B, I think it's a bit more challenging. We have let this be the the correlation coefficient. The standard bivariate normal random variables as a pair of px, I mean xy, whose distribution has joint probability of this function over here. Find the covariance of the two variables. Okay, so this one I'm gonna go first walk through um, the answer key and then another way to do it. So here we have x squared, like over here, we're just going to first focus on this part, in the part that's inside the, what is it called, the exponent. We have x squared of 2 minus x y plus y squared divided by this thing over here. We haven't put the negative sign here, but essentially that's the idea. And we kind of just group that. We see that x could be written as And then we just match the first two terms so that it works out that way. And we have to add the remaining part back so that we have the y squared because over here we have the um, low row of y, which we need to add back. So that's why we have this term just to add this part back. So the next what we have is that after determining this part, we have e of xy is equal to this thing over here. That's pretty standard definition. This is a pretty standard definition. And next what we have is that we just substituted the fxy of this long expression back into here, right? And over here we see, okay, we have this. We just sort of slightly simplify it so that we get to this point over here of what we just did. And now we're going to try to first evaluate, as always, the integral of the inner integral. So like this part over here. How we're going to evaluate this integral is that we see this is awfully familiar to the normal distribution, right? So the normal distribution, we can remind ourselves, look like this, is in this format of 1 divided by square root sigma square root 2 pi exponent of this thing over here. So essentially we can just match it. What is it? So like our thing would just be the mu would just be p of y, I mean rho of y, and then our variance would be 1 minus rho of squared. So then the normal distribution of the expected value from this thing to that thing would just be the mean. The mean is just this thing. So we can just simplify this whole thing as this thing. And then we plug it back into our outer integral, and we get that it's this thing over here. Now we're down to this expression. This again looks like a normal distribution, except the only thing here is that it's the second momentum because we see there's a y squared. So this is exactly matching the form of EY squared. So that's why over here, when I wrote this out, we have this is the standard normal, which in fact it's just when it's like the mu is 0 and the standard deviation is 1, we get this form. And then this form is exactly matching that, except we have the y squared, which means that this expression is just equal to e of y squared over here. And we don't know what this is, so we're going to use the standard variance equation. So then this would just be the variance of y plus the e of like the mu of y squared. So then we know that the variance in this, because it's standard, it matches the standard one. Our variance would be 1 and our expected value would be 0. So then 1 plus 0 squared is 1. So then our thing would just be the p of the coefficient in front. Yeah, so that's how we get over here. E of xy is equal to p, I mean rho, sorry. And then our ex and ey, we can just kind of find it. Basically, I could do e of x is equal to this thing of here. I did the exact same computation. I get this form of the inner integral. Then I plug this back in. And I realize this is an odd function because when I put in negative y, I get back the expression to the negative thing, right? So then this is an odd function. If we're summing it from negative infinity to infinity, then the odd function would just be a 0 because the left-hand side and the right-hand side would cancel out. It's because it's symmetric. So then our thing would definitely be 0. And the e of y could be the very same argument, except x and y are swapped in places. So then e of y would also be 0. So the covariance of exy minus ex times ey is just rho minus 0 times 0, which is rho. This is sort of the solutions way, proper way of doing it. I mean, a quicker way of doing it is kind of realizing, okay, it has already told us that this is a standard bivariate normal random variable, right? So that if we know this condition, we know the stuff, know our formulas, then we can sort of simplify the whole calculation over here by this way. So for any bivariate normal pair, the conditional distribution of x given y equal y is also normal. And especially for standard, when the mu of x is and mu of y is equal to 0, and the sigma of x and sigma of y is equal to 1. Sorry, this should be 1. Sorry, I should be correcting this. Um, this should be 1. Um, x given y equals y should follow a normal distribution with the variables as py and 1 minus, I mean not p, rho squared. So then we can start off the problem by obviously trying to find what e of xy is, because that's the main part. E of xy, we can use the Tower property to get e of xy given y. So then we can, since y is just a constant, we can extract this out so that we have e of y times e of x given y. And we know here that for the standard bivariate normal distribution, that e of x given y is this rho of y, right? So then our e of this thing would just be ey times rho of y. So then this we can rho is just a coefficient, so we can move it by the linearity of expectation. We can move it out, and then we have this thing over here, and we just do the exact same step as earlier, the variance plus e of y squared, and we get p rho of 1 plus 0 squared is this rho. Okay, this question was relatively difficult, but I think once you know it's a standard thing, then and you know the formulas, I think it's definitely doable. And the last question is actually much easier than I thought it would be, but obviously, I made some calculation mistakes. I think the main thing is just defining the variables so that it actually makes sense, so that you don't get confused. I don't confuse myself. So, in a Merck release recapture study, 4 of the 10 finches living in a certain sanctuary are briefly captured, numbered rings are attached to their legs, and released back into the wild. Assume that all finches behave identically and independently of each other, regardless of whether or not they're ringed. One finch is captured before it's inspected, a second one's captured, find the probability that the second one is ringed. So basically, the first given condition has absolutely no influence on what we know. So basically, that would still be the same probability of being banded. So there's 4 birds that are banded out of 10 in the population, so we have 0.4. In the second one, we are conditioned on the second being ringed. Find the probability that the first is also ringed. Okay, so this is, I don't really like the notation here. So I'm gonna kind of go to my own notation. So this is what I wrote. So the idea is that I just wrote this one, the first letter as like the first one, and then the second one as the second bird. So we know that we're trying to find the condition that the first bird is ringed, given, and we know that the second is already given to be ringed. So then this means that the second one has also to be ringed here. So then on the top we have both birds are ringed. And then on the bottom we can have a bit more flexibility with the second one being ringed and no condition on the first. So then the second one, I mean, if both birds are ringed, then we're just basically choosing 2 birds out of 4. And then for the other one, we are choosing it's the same one, and then we have also another case where 1 bird is ringed and 1 bird is not. The bird that is ringed is the second one. So then it would just be 4p2 divided by 4p2 plus 6 times 4, and I get 1/3 as my probability. I think that's pretty straightforward. Part 3. Um, Before they can be inspected, both finches are accidentally allowed to escape. Detector has recorded the number on one of the rings. Experience has shown that the detector has a probability of 0.9 of detecting any ring that is present, but it only stores the last number, so there's no way to know if it's 1 or 2 present. Given the information available, find the conditional distribution of the number of ring finches among the 2 that were captured. Okay, we're trying to find the conditional distribution finches among the 2 that were captured. Okay, so we know that like basically we have such a detector, and the detector is basically either right or wrong. Like if it detects, then it is right. Like it must have been meant that like um at least 0.9%, 90% of the time, it's actually like there was a ring. And if there was 2 rings, then the probability would even be lower. It would be 1 minus 0.1 times 0.1, because the only case that the ring there would be a false alarm would be that that both of the rings weren't detected, which would be very low. So that's kind of like a catch that I found. So that's kind of what we'll walk through how I would solve this problem. I think probably definitely defining the notation. So D is just basically like a true or false kind of flag of whether or not the detector detected the ring. And our B is just basically the number of rings that were actually present. So here we know that the detector would already detected something. So that must have meant that there was at least one or two rings. There's no case that there was no ring and there was a false alarm. That wouldn't happen. So we know that our P of given B equals 1 and B equals to 2 without any prior knowledge is that we have if a B was equal to 1, that means one of the birds had rings and the other didn't. So then out of the four birds that have ring, we choose one, and out of the other six birds, we choose another one. And now we could have chosen any of the two birds in the 10 population. So that's why we have 4 times 6 divided by 10, choose 2. And that gives us 8 over 15. And then for B equals to 2, both of them are chosen from the same, from the four ring birds. So then it's 4 times 3 divided by 2, divided by 10 times 9, which is just picking two birds and not caring about the order, divided by 2. So then we get 2 over 15. Next, what we do is we consider, okay, um, give like work or just going to be what is the likelihood that like we have just like one or two rings and then being detected, right? For that we just have PB equals 1 and D. So that would just be using conditional probability, that would just be PD given B equals 1 times PB of 1, PB equals 1. So then we know that the detector given that there's one ring is 0.9. That was given by the problem. And PB of 1, we just calculated this value, so we get this. Next, what we do is PDB equals to 2. So then this would just be this probability because um, there's four cases, right? I guess detect, 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 not detect, detect, not detect, detect, and not detect, not detect. And the only case that wouldn't work out is when both are not detected. So when both are not detected, it would just be having the probability of 1 minus 0.9 to because there's two rings, then it'd be squared, and then whatever is the remainder of that is just 1 minus this, which would be the one we want. So that's why we have this. And then this PB equals to 2, we just calculated and we get this. So by the law of total probability, we know that we could either have B equals 1 or B equals 2. They form a partition. So PD is equal to PD, B and 1, and B equals to 2. And we get that as 0.612. And then finally, we're trying to find, finally we got calculated all of this just because we want to find what PB equals 1 given D and PB equals to 2 given D is. This is just the conditional probability, which we just write PB equals 1 and D divided by PD. We just plug this in and we get 40 over 51. Since there's only two cases, one B is equal to 1 and B equals to 2, then the other one is just the complement of that. So 1 minus 40 divided by 51 is 1151 over 51. Okay, I think this question was just mainly just not confusing yourself and defining clearly what B and D are so that you can kind of work it out. Okay, that's it for today.